Let me get a roll started. Somebody erase mine. That's for whoever needs to do the makeup vectors quiz. This is it. You need to do it right now if you're here. But if you're not here, then maybe you're gonna miss it. Okay? Because we gotta get all this stuff wrapped up. I gotta catch up and return.
That's the one, when we was taking it, that you had to leave a few minutes early, we had to bring it to your office?
Yeah, I think so, yes. All right. And so we did have a makeup lab yesterday at 11 a.m. Okay. I know there was some misunderstanding, I guess. So we're gonna have to reschedule it. Okay. For the very last time. All right. But we need to get all this stuff wrapped up because we need to get, I need to get your grades back, get your papers and all that back. All right? But what we're gonna do today is we're gonna keep moving forward and we're gonna start talking about free body diagrams. All right? So a free body diagram. That's what we're talking about today. A free body diagram. Free body diagram. All right? So for most of the class, we've just been dealing with mathematics and we've been drawing cartoons, right? Here, we start with a cartoon and then we do mathematics based on our cartoon. So the first 3 chapters sort of prepped you for when I told you about drawing pictures and diagrams and things of that nature. That was to prep you for the free body diagram, okay? So the free body diagram goes like this, right? So we're gonna be talking about, so the first 3 chapters was dedicated to motion, right? How things move, and how things move, okay? And so now I said we in chapter 4, we're talking about, well, what causes things to move, okay? It's one thing for something to move, and then it's another thing for it to change its position from rest to motion or motion to rest. Either way, right? That's another thing. And that's where we get to forces. Okay? That's what causes things to move or to stop. So when we try to understand, or so when we get an idea of physics, and I know most people don't get physics till they get to college, especially here in Louisiana, we don't get physics until we get to college, right? But physics is the study of how the world works. And one fundamental aspect of the world is how you move through the world, right? How you get from A to B. Okay? That's very important. Because if you go from A to B, then you need to be able to get back to A. Okay? So we need to understand how things move through the world and what position they're in and blah, blah, blah. And like I said, so let's talk about the free body diagram, okay? And so we start with our box, okay? This is our box. So we're going to identify all of the forces which act upon an object in the world. So this is a box on the table, wherever, right? What acts upon this box? Gravity, definitely, right? So we draw. I like to draw a dot at the center, and then draw my arrow. In which direction does gravity act? Down, of course, right? So that's why I like to draw my arrow down, and then I like to call that F of G. What y'all think that stands for? Force of gravity. And we can calculate that. What is the force of gravity? We talked about it from the slides. Huh? No. It's what's the force of gravity here on the earth? You call it something else. When you get on the scale, you're measuring your weight. mg. That is the force of gravity. Right? And remember, this box is sitting on a surface. So here's our, well, right now we're gonna draw it. We're gonna draw it flat because we're gonna assume, because we're not moving, right? Even though friction is a thing that acts upon things that's sitting still, right? We normally, or the untrained mind associates friction with things moving past each other, right? But when I sit something on the surface, right, there is a force of friction which keeps it in place, right? Because what if this was ice and I sat it on there? What would it do? It wouldn't slide. It might not. Well, if we put it right here, maybe it'd slide off. Yes. But we know it's going to slide around. Why doesn't it slide around here? The friction is holding it in place. The friction of this between this and the table. Okay. So, but we're not at friction yet. Okay. So, what is the other force? Remember what I said. When we set something on a surface, it puts the force of weight on that surface, right? Just like when I set this computer on this table, the force of gravity pulling the computer towards the earth is pulling it down. So what's stopping it from going down? The force of the table is pushing back up on it. And what do we call that force? Starts with an N. The normal force. It's called the normal force. Right? That was, remember the slide with Abraham Lincoln statue from the lecture slides? And I'm gonna post the narrated slides for you. We call that F of N. That's the normal force. Normal, right? So now imagine if I had, let's say in this case, we're talking about the box. Let me draw it like this. Imagine if I had a person pushing on the box, right? We're gonna call that F of A. F of A is the applied force. The force applied to the box by the person or whatever is applying the force. Gravity acts down, right?
Yeah.
So this is an applied force. This is like you pushing the box. So what opposes you when you push the box? Friction. Yes. That's what we just talked about. So friction is this way, right? And we call that F of mu of S. And we have two types of friction. We have mu of S, which is static friction. And we have mu of K, which is kinetic friction. Okay? So, we have to overcome the static friction first. Okay? Before the box can move. Once we overcome the static friction, then the kinetic friction kicks in. And you guys know that to be true, right? Because isn't it easier to move an object once you get it moving? Right? It's easier. It's harder to get it going. That's because you're overcoming the static friction. Once you overcome that, then you get to the kinetic friction, which is normally much smaller than the static friction. And we're going to show that in the mathematics. Right? So, in this case, we have what? How many forces on the box? 4. We have four forces acting on the box simultaneously. Okay? And so, when forces, maybe I shouldn't do it like that. Maybe I should do it like this. Make it consistent. Okay?
What's the alphabet again?
Applied force. Okay? So now the next step, right, is remember I said about the tug of wars. What happens with the tug of wars? Somebody explain to me what happens with a tug of war. Huh? All right, and what happens to the flag in the center when one force is larger than the other one?
It's pulled that way.
Okay, so what's happening here? We have four forces acting on the box. Right? So, does the box move up or down? Huh? In this situation, I'm asking about this situation.
If they're all equal, all the forces are.
No, it's sitting on that surface. So is it possible for it to move up or down? No. So what must that mean?
It's either left or right.
No. Think about the tug of war. The tug of war. So if it doesn't move, the flag doesn't move, what does that mean? The forces are equal. The forces on each side are equal to each other. So that means because the box doesn't move up or down like the flag on the tug of war, that means that these two forces must be equal to each other. That's called summation of forces in the X, summation of forces in the Y. Sigma. That's a Greek term, right? Right? We got sigma, we got theta, we got all that. All them Greek terms.
Wait, so those two symbols mean that they're equal? Like,
Huh?
those two symbols mean that?
No, those two symbols mean that we're summing the forces in the X. Sigma means sum.
So it's like
So we're adding the forces together. We're summing. Sum means to add together. But because forces are vectors, we know that they have what? Magnitude and direction. So we have to indicate their directions. So that means that these two do what? Huh? Cancel each other out. So our sum of the forces in the y direction equals to what?
0.
0. So we write that mathematically because f of n is pointing up. That's positive. And f of g is pointing down. That's negative. We write f of n first minus f of g equals 0. So because this expression is true, then mathematically we can say what? They're equal. Because they equal to 0. 6 minus 6 is what? 0. A minus A is 0. Doesn't matter that it's f of n and f of g. They equal to 0. So math dictates that they must be equal. Okay? That's not physics, that's math.
So they'll always be equal?
No, they won't always be equal. Nope. No indeed. That's the hard part of, well, that is the hard part of the free body diagram, but it's really not hard at all once you understand what's going on. It's the difference is whether the object is moving or not. This is the only two situations, right? That's the only two situations there are. It's either sitting still or it's doing what? Moving. That's it. It can be one or the other. Can't be nothing in between. Unless we're talking about quantum mechanics, which is physics 435, which is not for this, not for non-physics majors. Okay? So what you got?
So just to make sure I'm clear,
Yeah.
if an object is still, like it's on a table, the force of gravity and the normal force would cancel each other out.
Yes. If it's sitting still.
Okay.
So if it's not sitting still, then it means it's moving.
Right.
It's either crashing through the table or it's moving up. Right? So in the case of an elevator, right, we can either go what? Up or down. Of course, this can either, the only way this can really go is what? Down. Because of gravity. But an elevator can go up or down. See that? Okay?
Wait. Just to make sure I'm
Yeah.
understanding. So
I like questions. I
so
like
for the
questions.
elevator, since it's moving up or down, would the applied force and
Well, that's in, but
the
see, that's
kinetic
in,
friction that would cancel each other out?
no, we're not talking about that yet. We're only talking what?
Up and down?
Up and down. We're only talking about y. Remember what we did in chapter 3? We separated x and
Why?
y. When we started talking about vectors, we separated x and y. So now we're more specific in what we're saying. We're saying either we're moving in the x or we're moving in the y. At first we just was one-dimensional motion. We said or we could be moving what? At the same time. When we get on the inclined plane, we're moving in the x and the y at the same time. That's a different type of motion, right? Because we started off talking about what? Free fall, which is straight down. Or motion like this, like a car, you driving home from school, right? Remember that problem?
Yeah.
That was like this, that's x. Free fall, right? The lab we did, right? When you drop the ball, that's one-dimensional motion. Then we talked about vectors. So we said, now we're talking about x and y at the same time. So we could do that with force, because force is a vector. Okay, so now we have broken it up to X and Y. And that's what we're gonna deal with right here, right? So that's good. So now, since we dealt with this, now we can write an equation for the sum of the forces in the X direction, right? So, so a lot of times in the problem, it will tell you whether or not the box is moving or not. Okay? So in this case, the first case, we're going to assume that the box is not moving. So in that case, that means that what? Because we remember the box is the flag at the center of the tug of war. So what does that mean? If the box is not moving this way or that way, what does it mean? They are equal. This is physics. That's how simple this is. And people think it's so hard. Oh, I'm about to die, I gotta take physics. It's a tug of war. That's it. This is how I learned it. And I never looked back. When I got this down pat, this was like child's play. Like what? This is what people was dropping the class 3 and 4 times for? Okay? So, we can write an equation, and we can say what? So, in this case, since we're on the X, we're gonna say what? Going to the right is what? Positive. Going to the left is negative. So then, if f of A points to the right, then we're gonna write that one first and make it positive. So f of A minus f of mu of S is equal to 0. Because all of the forces are equilibrated. That means that the box is not moving. That's what that means. Okay? And so, based on these two equations, we can solve certain things, right? Okay? So what will normally happen in the problem, and we're gonna work some problems, right? So we're gonna have some real problems to work. But I just wanted to go through this, right? It'll give you what's the mass of the box. That'll be given in the problem, right? So M will be given, right? M, let's say is 10 kilograms, okay? The mass of the box is 10 kilograms, okay? So from here, we know that what? We know that, we just said that what? These two are equal. So we can come here and write what? F of N is equal to what? F of G, and F of G is equal to what?
10.
Not 10, huh? 10 times G, right? M times G. So now we can calculate what F of N is and what F of G, because they're both the same thing. They have to be in order for the box to remain still. If one exceeds the other, then the box will move in that direction, like the tug of war. This is it. It's that simple. Every time. There's no exceptions. That's why laws, remember we talked about that in the beginning of the semester about laws, Newton's laws. That's why laws are so powerful. But they have to be tested and tested and tested and tested over and over and over again. And that's what has happened with Newton's laws, right? So now we can calculate M times G, or F of N, which is M times G, okay? And a lot of times, right, the applied force will be given to it, okay? So in this case, let's say we applied 2 newtons, which is not a lot of force, right? Because 2 newtons, just based on my experience, I don't think that's enough force to move a 10 kilogram box. It's not enough force. So this expression should hold up under these conditions, under these numbers, right? So let's say it's 2 newtons, right? And so you'll have F of A right there, right? But you know that F of A, right, is what? What else do we know? F of A is also what? Equal to F of M of S, right? Right? And in this case, we have to make sort of a caveat, right? Because we're talking about the applied force, right? So we can apply 2 newtons and the box doesn't move, right? So we can also apply, and we're gonna do this mathematically so I can show you how this works. And maybe we'll have a problem like this where you can see mathematically how it works, right? But we have to make a caveat here, and we have to say F is either smaller than or equal to. Why? Because we can have a number of forces that are smaller where the box doesn't move, right? But there's a certain force that once we apply that amount of force, the box is gonna move. Y'all following what I'm saying? There is a range. There's not a there's a lower range, I should say, or there's a limit, right? When I push something, right? Right? I could be pushing right now. I'm just not pushing what? Hard enough for it to move. But I'm applying a force now. I could push a little harder. And still what? It doesn't move. So that's 2 different forces. So that's why we gotta say the applied force is either what? Either smaller than or equal to the friction force. Right? Because it could be all of those forces smaller than up to the friction force. But once we exceed the friction force, then the what? Box is gonna do what? Move. All right, so we're gonna work on some, like I said, we're gonna work on some, oh, it's kinda early. So my next class sample is evaporate. All right, hello, it's Kathy from students. Yeah, so obviously the second scenario we're gonna work on is what? When the box moves, okay? And that's in the Y and in the X. Because like I said, we're gonna talk about an elevator, right? An elevator is a certain type of simple machine, right? It's called the Atwood machine. An Atwood machine, okay? So, like I told you, simple machines, what's the point of a simple machine? Let's see who remembers what.
Makes your life easier.
Makes your life easier. It does work for you. That's what the point of a simple machine is, right? So when you, instead of walking up the stairs, you jump in the elevator, right? Okay, so the elevator, matter of fact, the elevator only moves what? Up and down. Doesn't move side to side. Well, they got some cases where we're gonna talk about. We can talk about certain machines where They are attached, and one moves like this, and one moves like this, right? Those machines, a lot of times, are doing work that maybe 100 years ago, people or individuals had to do that work, right? They're doing work. So simple machines are very, very powerful, right? And that's basically where we're leading up to, okay? Or one aspect of where we're leading up to, right, is doing work, okay? Because in order to do work, we need a force, right? When we look at the equation of work, work is force times distance. So in order to do work, wherever it is, whatever work it is, the work that it takes for you to get up and come to this class every day from wherever you sleep, for you to get from wherever you sleep to here, you had to do work. Okay? Or something had to do work. Whether it was your car had to do work. Right? You have to put gasoline in your car. That's the reason why you got to put gasoline in your car, because your car has to do work. And it's doing the work for you. Because otherwise, how would you get here? Walking. Exactly. You walk to school every day. So the simple machine makes your life easier. So let's see, I don't think we got time really to go into that second scenario, because I really want to, yeah, like we're gonna say it. I think this is enough for today. Any questions about this? I saw we had a few more questions today than we normally have, which is interesting and exciting. I like that.
I have a question.
Yes.
So if the static friction is more than the applied force, right?
Yes.
Static, whatever,
Yes.
it just won't move.
It just won't move.
But if the gravitational force is bigger than the normal force, it'll fall. It's gonna move first.
Yes.
Okay.
Yes, indeed. Yep. That's it. It's the same principle, just in different directions, right? Same principle in different directions, right? It's just normally, that's why I kept talking about the elevator, because the elevator goes up and down. See, normally most things just go what? Crash down, right? Like here, sitting on the table, it's not just gonna magically come up, right? But it'll crash down, definitely, right? But in this direction, in the X, we can go what? Either way. Either way, right? Now, because this force is bigger than this force, is not gonna just start moving this way. It's just gonna prevent this from moving that way. Following me?
Yeah.
And so, there will be instances where we have additional forces, right? Where, so, this could be attached, right? This could be attached to a rope, right? That could be attached to a rope. Let's say this is another type of machine, right? This is attached to a rope. We have a pulley right here, right? Come down, attached to another block, right? And, right? Obviously this one pulls this one this way due to its weight, and then this one pulls this one back up, right? It can have some other force pushing it back this way. You see what I'm saying? So, this one, so in this case, right, then you'll have the friction force, and it'll be K, right? This is moving, right? And it'll be a tension force, right? So here you'll have two forces, right? So here, the tension will act like that due to this rope, right? When you tie a rope to something or a tether or something like that, right? And you pull it, you put in a force, right? And you're putting the force on the rope first, and then the rope puts the force on whatever it is you're pulling. So that rope, in order for you to see that thing move, that rope has to do what? Get tight. It has to tension. It has to tense, right? That's where you get tension from. So tenses up, pulls, right? So when this thing goes down, this thing pulls, right? And the tension, right, retards that force, just like the friction. Follow me? But we're gonna work on it. It's like, that's why I say let's get this right here. Let's get this together. All right. This is one scenario. Let's don't confuse them all, because it's a lot of different things that can happen. Okay. Let's just work on the simple box on the surface. That's it. All right. And that was mu of s. All right. Let's get that simple one down first, and then we work on more complicated situations. But this one right here is this is the one we need to get first. All right? I think that's it. Is it 12:43? 12:40, about 12:40, that's it. All right, so I'll see y'all on Monday.
So for the free fall ride, the makeup, do we come on Tuesday or do we come back on Thursday? And like what time?
Well, on Tuesday, so apparently, so I guess, listen, I guess since y'all already have that time allotted in your schedule, then we'll do it at the same time, okay?
On
Next
Tuesday.
Thursday.
Oh, on Thursday.
Yeah, cause
Okay.
Tuesday we doing another lab.
Okay.
Yeah.
I just want to be.
Yeah. We doing another, we gotta do projectile motion on Tuesday. Yeah,
Tuesdays in person or is it online?
in person,
In person.
in person, yep. Yes, indeed. We should still be in here. I mean, they ain't gonna knock the building down over the weekend.
Okay.
So we should still be here Tuesday.
Okay.
We got all our stuff moved out, but we still in the building.
Okay.
Yeah.
So what do we, that's for the vector lab?
No, this is the vector quiz that
Oh,
that
my bad.